Next up, we have David Huggins, who is my new colleague across the street over at the Therapeutic Development Initiative at Weill Cornell. We're super excited to have him, and he's going to tell us a little bit about making free energy calculations interpretable, especially in terms of things like hydration free energies.
Thank you very much. So, just an overview of the talk. So I've recently moved over from the University of Cambridge, and the work I'll talk about today is from the University of Cambridge to the Therapeutics Discovery Institute based at Weill Cornell Medicine. So I'm interested in applications of free energy methods, and in particular, kind of interpretability and how you kind of decompose these free energy changes into atomic or group contributions. Is that meaningful? Is it useful? So our approach is to start with the Svansk equation, and I worked with a PhD student, Ben Irwin, to do this. I kind of set him this problem, and he went away and spent a long time thinking about it. I'll discuss the approximations or the assumptions that we used in the derivation, and then a few applications to see does this fit with our intuition in terms of hydration free energies and binding free energy. I'm using absolute binding free energies in this case. And then just some ideas on future developments. So I'm using alchemical binding free energy calculations in my work at the TDI, and they've proving more and more useful in drug discovery for predicting affinities. But the problem really is, even if you had a perfect force field and perfect sampling, you still need good ideas as well, right? So if everything you design is bad, you might be happy, but your colleagues, medchem colleagues, are not going to be particularly happy if you can't design anything that's good. And from a given starting point, there's a huge number of different molecules that you can make. So having some kind of idea of why something binds rather than whether it binds would be very useful. So rather than doing a set of 100 calculations, if you can do one and get some sense of why whether this is good or bad, you can take that forwards. And I've put a little star here because in this case we're working out why the force field thinks that this molecule binds, not necessarily why it actually binds, but I mean that's a separate talk, a separate issue. And so thinking about some previous work that I've done on water molecules, so this is looking at water molecules in protein cavities, singles or pairs of waters, and using this inhomogeneous fluid solvation theory to assign kind of free energies contributions to individual water molecules. This is the same idea that underlies WaterMap. If you can do this and get some kind of accurate or predictive or useful answer, could you apply something similar to these alchemical free energy calculations? Can you get something meaningful out of that? So I'm not going to go through the entire kind of derivation, but I'm going to kind of give you a flavor of the approach that we used here. So you can write your the energy for your system in terms of your non-bonded interactions, typically in terms of this pairwise additive energy function, where you sum over all pairs of atoms. You could rewrite this in terms of the energy of individual atoms, where that energy is just half its interaction with every other atom in the system. We're now going to take the Svansk equation as it's kind of typically written, and we're going to rewrite this in terms of these kind of contributions from individual atoms. So this is now a sum over the interactions of all the individual atoms. And so the problem I set Ben was to take this and kind of expand this out and see where it goes. And so the approach is to take this Maclaurin series for this kind of exponential term here that's inside the ensemble average, and you expand it out in this way. You now have a sum of terms, essentially have a power series here. You can apply this multinomial expansion to the sum of energy terms, and you get this horrible looking at kind of infinite sum, which is essentially made up of kind of first order terms, second order kind of squared terms, cubic terms, all the way up. And the kind of approximation or assumption that we're going to make, or the model that we're going to use, is that if you consider one of these terms inside here, it might look like this, with contributions from atom I, J, and K. Different contributions will be raised to different powers, and so then we're going to separate these out based on these kind of exponents here. So this is sum of 4 halves going to go to atom I, quarter to atom J, and quarter to atom K. and then we can group all the terms assigned to each atom. So we're just taking this huge expansion and partitioning it out into different terms that we assign to different atoms. So I'm not going to go through the rest of the proof, but that's really the kind of trick or the assumption, so approximation that we make. When you do that, we can manipulate that, and we're not going to truncate. That's the important thing. So we've got all these kind of infinite sums. We're not going to truncate at any point. We just manipulate through to get this expression for the kind of estimate of the free energy contribution of each individual atom in the system. So this comes out like this, where this is the total free energy change for the whole, whatever change you're looking at. So we can calculate this using any method we want. So we're using bar for this. And then this term, we have to go in and look at all of the individual lambda windows, look at the contributions from each lambda window to this term. And then we're kind of assigning a portion of this total free energy change based on the differences between applying different Hamiltonians. So this has just been published a week or so ago. So in terms of interpretation, I mean, the physics is kind of questionable. It's not a unique decomposition of the free energy. You could think about doing it in lots of different ways. And it's kind of not thermodynamically rigorous. It makes, it makes me a little uneasy and people a little uneasy, but it is possibly useful. So that's what we're going to look at next. So you can apply it to standard energy trajectory from FEP calculations, so you don't need to do anything else on top of the free energy calculations that you've already done. And so we're post-processing to calculate these numbers. You can't use, it has to be pairwise additive. You can't use PME electrostatics, but you can apply it to a trajectory from PME simulations. And so you just make a switch or a shifting function. You can apply that to the trajectories. Okay, so we're going to do a sanity check first, which is looking at hydration free energies of some sort of simple molecules. I'm using NAMD, the CGNFF force field with, for some of the more complicated molecules, ParamChem, TIP3P water with PME. I'm using 32 lambda windows and 2 nanoseconds per window. And in this case, I'm using fixed solute atoms. That was just a choice that we made. We wanted to look at how that made a difference. These are the experiment versus predicted hydration free energy changes, just to show that these are in line with experiment. So then you can go ahead and, I mean, it's simple to kind of color based on these kind of contributions. And so this is methane, hydrophobic, unfavorable, but you can kind of decompose this into the contributions of the hydrogen atoms versus the carbons. Methanol kind of makes sense. You've got a very kind of polar oxygen that makes the majority of the favorable interactions. Actually, in this case, the hydrogen makes an unfavorable contribution. That seems to be because the oxygen has the kind of most, the largest kind of charge in the system, pulls the hydrogens from the water in towards it, which then make kind of unfavorable electrostatic interactions with the hydrogen. And similarly, so this is just a sanity check to make sure, does this fit with our intuition? And I guess, yes, it does, right? So the more polar molecules, the polar atoms are the ones that are important. The 4 hydrogens here should be exactly the same because they're symmetry related. There are slight differences here, probably due to sampling, or possibly, slight differences in bond length based on the fact that our PDB has only 3 significant figures. There might be slightly different bond lengths. They're going to be the same. What I'll note here actually is that what you see, interestingly, if you're eagle-eyed, you will have spotted that some of these contributions here is not equal to the total free energy change. That's because half of the hydration free energy ends up being assigned to the water molecules in the system. And that's because pair interaction energies, as I said, are shared half and half between the 2 atoms. When you're coupling or decoupling a water, the only interactions that you're coupling or decoupling are between the water and the solute. And so you end up assigning that half of the free energy change to the water. So what we end up doing is assigning all water molecules to one big group. So we don't calculate individual waters because they're all indistinguishable. But you can see, so this is an example of what you get if you run the simulation for a very short time. You see the waters are not kind of equivalent to each other. You need to run for a long time to make them average out over all their possible different orientations. But I guess this brings another point that we can use here and we have used is to group together indistinguishable atoms. And so, the hydrogens on a methyl group, if it's rotating, are going to be indistinguishable. You could just group them all together if you wanted to. I'll show you back again. In this case, because we fixed these atoms, these two hydrogens are in a different environment to this one, so they have a different contribution. But if we'd let everything rotate, they'd average out over their different positions that they adopt. Okay, we're all thinking about caffeine at this point, and so that was the next molecule that I looked at, or that we looked at, just to look at a slightly more complex molecule to see what happens then. So in this case, you can see kind of you've got the methyl groups here that are overall kind of hydrophobic. When you kind of sum together the entire contribution, it becomes a little more complicated. You think a carbonyl group like this, the kind of oxygen atom here is favorable towards the hydration. The carbon that it's bound to is not, has the opposite charge. So overall, you could think, well, this net contribution is unfavorable, but then you've got kind of atoms that are joined to it. So there are some subtleties here in what you take from this, but at least again, this fits with our intuition. This is the most kind of solvent exposed and polar atom. It makes the strongest contribution to the hydration free energy. Some nice properties of this as well. So when you're calculating these contributions, they actually converge extremely quickly because you're just looking at an individual atom in the system. So even after about kind of 200 picoseconds, these can converge. I should warn, obviously, this is just for solvation, where there's no kind of major kinetic barriers here. These values are going to converge with the total delta G, and they're going to be equally dependent on pore sampling. So if there's kinetic barriers, this is not going to address that in any way. You're going to still make the same mistakes you make with just calculating the overall free energy change. So we then moved on to looking at the binding free energy. In this case, we picked lopinavir and HIV protease. These are two molecules I've kind of worked on in the past. That was why we picked this system. It's kind of well studied. This is not a picture of HIV protease, so don't. So yeah, this was just the picture I had to hand. The way that we do our binding free energy, absolute binding free energy, we're actually doing this all in one box. So we separate the two the complex and the unbound ligand by about 40 or 50 angstroms. Doesn't have to be done that way. This is just how we did it. You take your unbound ligand and your bound ligand. We're going to switch on the van der Waals of the bound ligand first with restraints. We're then going to swap the charges between the two bound and unbound systems, and then we're going to switch off the van der Waals of the unbound ligand. Okay, so we can sum our kind of terms here. We get our analytical correction term, and then we calculate the energy of switching on or off these these restraints using thermodynamic integration. This potentially presents a problem. You obviously don't. If you restrain the molecule too strongly, you're going to perturb the actual kind of natural dynamics. So we wanted to make this as small as possible, and we're using restraints similar to this kind of Boresh approach, where we use a distance, angle, and a dihedral restraint. The overall number is not great compared with experiment, but we'll move ahead and kind of gloss over that. It's not too bad. And so we now have a slightly different situation where rather than just looking at kind of one change, for the ligand, what we really care about is the difference between the coupling in the binding site and the coupling in the solvent. So we have to look at the desolvation penalty as well as the kind of interactions that are then made by the ligand. So the way that we do this is we look at your kind of contributions from when you couple in solvent. So again, this is like essentially the hydration free energy of lopinavir. And then we look at coupling in the binding site, all the interactions made there. Overall, then we kind of just sum those contributions together. So we're getting an overall balance between desolvation and interactions in the binding site to give kind of which atoms or which groups make the most favorable contributions. And you can see, for the most part, it's obviously the kind of polar hydrogen bonding interactions that are giving you the majority of your contribution. And then there's a kind of spread of contributions across the nonpolar or the hydrophobic atoms. You can also consider the contribution of the protein atoms if you want to. So this is just a kind of simple picture. So you've got lopinavir in green here, and I've just colored the protein atoms that make a kind of significant contribution. So it's the atoms that pair up with the hydrogen bonding groups in lopinavir for the most part. And then you've got a couple of kind of additional atoms, but they're a bit further away. And this potentially could be useful for identifying kind of more long-range or allosteric effects. If you disrupt an interaction that's far from the binding site, you're going to see that. So a couple of advantages of this kind of technique. It's relatively simple to compute. You can apply it to any alchemical transformation that you want, and it's applicable to standard trajectory from FEP calculations. So I've done this in NAMD as post-processing tool, but I mean, it's as long as you can calculate these energies, you can do this for any simulation. And the atomic contributions are kind of in line with intuition. So that's always a nice to have. And I mean, there's more work to do, but this potentially provides design principles to improve desired properties. And so you could think about, which groups you might want to change in a ligand to improve the contacts. If you want to remove a hydrogen bond because you've got too many hydrogen bond donors, which one's the one to remove? Which one should you target? So it gives you some kind of design principles to work from. The disadvantage of things to work on, this decomposition is not unique. So you could do the decomposition in lots of different ways. You'd still kind of sum to the total free energy, but would it be correct or useful? This is not thermodynamically rigorous. Assigning free energies to atoms, and even assigning energies to atoms is questionable due to kind of the many-body effects that you get here. In addition, talking to some of the guys from Schrödinger, there's a suggestion that you may be sensitive to the pathway or the lambda schedule that you use here. So if you use a different lambda schedule, a different pathway, you're going to get potentially different predictions for which atoms are more or less important. That's something that I haven't explored. I can't really comment on. In addition, it's not always easy to interpret or act on, at least in its current form. So as I mentioned, for the case of kind of caffeine, atoms can be predicted to be kind of favorable, but the group that they're in overall is not. So how do you make sense of that? How do you act on that? So that there's more I'd like to do with this, and there's a lot of thinking to do. So I think this could be useful in the context of relative binding free energies, but there's a few developments or changes that might need to be made in order to do that. There's some interesting things about convergence that you can use. So an indistinguishable atom or a symmetry-related atom, they should all give the same answer if you've got good sampling, so you can monitor that. So we've looked at the kind of individual water contributions and how they change over the course of the simulation. They should all converge to the same number, and that could be some kind of measure of convergence. And yes, as I said, what is the effect of the alchemical pathway or lambda schedule on the predictions? Does it make a difference, or is it insensitive? So in conclusion, Ben and I have worked on developing a new approach to assess the contribution of individual atoms or groups of atoms to a free energy change. So we've done this by manipulating the Svanzing equation, trying to use minimal assumptions. We've tested it using hydration free energies and binding free energies, and the results are in line with at least my intuition about thermodynamic driving forces. There's further work that's needed on how you interpret, how you might want to apply the method in a drug design context. So my acknowledgements, I guess that the main ones have to go to Ben, who did the majority of the kind of heavy lifting on the mathematical side, Department of Physics in Cambridge, but also Mike Payne, Sinisha Vukovic, and Alex Wade, and these three guys are in my group. Also a number of collaborators at the Department of Chemistry, Biochemistry, and the MRC Cancer Research Center. Also, thank you very much to the conference organizers, and thanks very much for your attention.
Questions? Yes, Shirley.
So, I'm not going to guess your age, but in the 80s, there was this thermodynamic component analysis and thermodynamics by Bruce Teeter, et cetera. I mean, can you say something about the difference between what you're doing, what they did 30 years ago?
So, I mean, I know Bruce very well, obviously, but I'm not familiar with that particular work, so maybe you can point me in that direction.
His big paper had hidden thermodynamics as the first part of the title, and beyond that, I could probably look them up, but I think with hidden thermodynamics and Bruce Teeter, in the mid-'80s, you could probably find it as well. But there was a big focus on this component analysis and looking at contributions from individuals. Try to use this to guide exactly the kinds of objectives you were talking about, and I don't remember the details of the formulations they had before, but they're similar in many ways to, I think, what you were discussing about in spirit, and so it might be useful to...
Yeah. Was that implicit solvent? Was that implicit solvent or explicit? Was that implicit solvent he used, or it was all explicit? Okay.
Early days of free energy methods.
Sure. Thanks.
I had a quick question. Caffeine is Caffeine is suggested to form higher order molecular structures in water. Do you expect the atomic contribution to actually significantly change if you look at these molecular assemblies of caffeine?
Yeah, I mean, I guess it depends what change you're looking at. But yeah, if you put multiple different caffeine molecules in the simulation and they interacted, then you would be able to, you should be able to see those changes.
One more in the back.
Yeah, nice talk. Could you say something more about the potential application? Have you never thought to use this kind of mapping maybe to derive feature for maybe developing pharmacophore models and stuff like that? Because the kind of information that you may provide could be extremely useful for identify which are the most important region in a ligand.
Yeah, absolutely. I mean, if you looked at contributions to different regions of the binding site, you could kind of sum them and see which potentially are going to give you be hotspots for binding. I mean, the ways that I've thought about using it are for optimization. So you have kind of a number of different methyl groups in this. So kind of which methyl group is the most dispensable, but you could flip that and say which is the most important as well. So yeah, which we would keep.
Really, the last one, have you tried maybe to calibrate your approach, maybe taking some data set from 3 weeks of analysis and see somehow you can try to correlate if a specific group or atom is important for activity. So there is a kind of correlation between atomistic simulation and user style model that maybe can allow you to verify if your method has a particle application for drug design as well.
Yeah, absolutely. I mean, there's lots that one could do with this, and that's certainly one thing that would be useful. Yeah.
All right. Speaking of caffeine, let's